In this last segment, we're going to look at the problem of testing whether a given graph is bipartite or not. And of course, we are again in the dense graph model, which means that the type of queries we can ask are of the form, is there an edge between these two vertices, say U and V? And using those queries, we must answer the question whether the graph is bipartite. And let's remind ourselves what we mean by a graph being a bipartite graph. Such a graph must have a partition of its vertices into sets V1 and V2, such that the edges are a subset of V1 cross V2. So the edges can only be of the form where they connect one vertex from V1 and one vertex from V2. But unlike the biclic, it doesn't have to be exactly V1 cross V2. And a well-known property of bipartite graphs is that there does not exist any R-length cycle in the graph G. In fact, these two statements are equivalent. The statement that G is a bipartite graph is equivalent to saying that the graph does not have an R-length cycle. And exploiting this property, we can arrive at a linear time, shall we say, BFS-based algorithm for testing bipartiteness. Basically, just tests whether there is any cycle that is of odd length in it. Okay. But obviously, this will not suffice for our purpose because executing BFS would mean that that we need linear time and linear number of queries, and that's not acceptable. And so we have to be in the realm of sublinear testing. And for this purpose, we will need a promise. And the promise should be that either the graph G is bipartite or it's epsilon far from being a bipartite graph, which means that more than epsilon n squared edges must be removed in order to make the graph bipartite. Okay. Notice that we only need to remove edges in order to make it bipartite, because we really don't need to add any new edge, because for a bipartite graph, the edge set E only has to be a subset of V1 cross V2. And as we mentioned earlier, we're only allowed queries of the form, is there an edge between two vertices, say vertex U and vertex V? So let's, without further ado, look at the algorithm to test whether the graph is bipartite in this sublinear setting. So the algorithm is very simple. We simply sample theta of 1 over epsilon squared times log 1 over epsilon number of vertices uniformly at random. The constants hidden within the theta notation can be reverse engineered later, so we're not going to worry too much about constants. In fact, this whole segment we're going to purposefully be a bit sloppy in order to focus on understanding what's going on, and we will work out these constants as part of our exercise later. So we sample these many vertices, and after we've sampled these vertices, we will query all possible pairs of vertices from this sample, and by doing that, we will construct the induced subgraph of those sampled vertices. And then we'll just test whether that induced subgraph is a bipartite graph or not. And this we can do using BFS. Remember, we have a linear time algorithm using BFS, but notice that this is a linear time algorithm on a graph that's of size roughly square of epsilon to the minus 2 log 1 over epsilon. And so that's still very much sublinear in terms of the larger graph that we're concerned about. Okay. Now we test the bipartiteness of this induced subgraph, and if it is bipartite, we accept, otherwise we reject. And of course, the verdict of accept or reject must hold in the larger input graph on n vertices. So you may wonder, where is the enforce part? In the biclic case, we had a clear enforce step and a test step. As it turns out, in this case, the enforce step and the test step are both blended, and really it's only in the analysis that we separate them out. Okay, so we'll see that in a little while, but for now, let's on purpose make a misstep, a wrong attempt, if you will, just to sort of get a sense for why we even need this enforce and test approach to analyzing this algorithm. Notice, of course, that the algorithm is always going to be correct when G is bipartite. And so, like in many other such property testing contexts, we don't care so much about getting the right answer when the property holds. We're more concerned about being able to reject when the property does not hold. So for that purpose, we're going to assume that the graph G is epsilon far from being bipartite. And now we have to show that the algorithm will reject such a graph with some good probability. Okay. Under that assumption, consider a partition V1, V2. We're guaranteed that there are more than epsilon n squared violating edges. And these are edges that are going between vertices that are both in V1 or both in V2. Here's a quick exercise for you. What you need to show that if you sample 1 over epsilon times log 1 over delta samples, you will hit such a violating edge with probability at least 1 minus delta. So for this, you will have to look at the probability that each sample, and here we're sampling edges in some sense, each sample will be a violating edge with probability epsilon, and so within each sample will not be a violating edge with probability 1 minus epsilon, and we have a 1 over epsilon times log 1 over delta such samples. So what is the probability that all of them don't reveal a violating edge? That will be, we need to show that that will be of probability delta. So with probability 1 minus delta, we will be able to find a violating edge. So spend some time to work out those details. But once you've convinced yourself that that's the case, let's step back and look at what we have achieved. We have shown for a specific partition that we will be able to hit a violating edge with probability at least 1 minus delta. That's great for one partition, but we really need to be concerned about every possible partition. And here lies the problem, because the number of partitions is 2 raised to the cardinality of the vertex set. And union bound is the only option at our disposal right now, and that's not going to work. So the probability of failing is at most delta, but then if you multiply 2 raised to the cardinality of v times delta and still want that to be a small constants, then delta must be extremely small. And if you think about it, if delta has to be uh, like 1 over 2 raised to the cardinality of v, then log of 1 over delta is going to be log of 2 raised to the cardinality of v, and that's going to be a linear number of samples, linear in the number of vertices. And that's just an unacceptable number of samples. We want our algorithm to be able to operate under a far fewer number of samples. So, with that being the case, we have to think about how um, we can have an enforce part and then test against what is being enforced in the enforce part. So this leads us to the second correct attempt. Uh, okay, so just a little quick post-mortem on attempt 1, the failed attempt. We were not able to rein in the 2 power cardinality of v number of degrees of freedom that we had in partitioning the vertex set. Uh, it's so we have, but there's a lot of structure which we need to be able to exploit. And so the way we're going to do that is the following. Remember, the enforced part is implicit. What we're going to do is just treat the first few queries as enforcer queries, and those first few queries will create a structure, and then the rest will be used to test against that structure. And this is quite nicely analogous to the balls and bins way of analyzing that we had before. The algorithm, I mean, the process was the same for all 2 squared of n number of balls. But for the analysis purposes, we set the first square root of n balls separately, created a structure, and then looked at what happened when we threw the next square root of n balls. And what we're doing here is very similar. The first few queries we're going to enforce a structure, and then on even though the algorithm doesn't change, in the analysis we look at the structure that is enforced by the first few queries, and then use the subsequent queries to test against that enforced structure. So let's look at it a bit more carefully. So we're going to call the set of first theta of 1 over epsilon log 1 over epsilon queries as the set U. This is the part that's going to enforce the structure. Okay, and let's pick a bipartition U1, U2 of the set U. And so the moment we have a U1 and a U2, we're going to assume that U1 and U2 are chosen such that there are no edges between vertices in U1 or no edges between vertices in U2. If we cannot find such a partition, then we're already done. The graph is no longer a bipartite graph. So we found a violation. But let's assume that we could not find a violation. And so we have this U1 and U2. How could we subsequently find, and this creates a structure. Some vertices are now in the left in U1 and some vertices are in the right in U2. There are a lot more vertices in the graph. But how do we find a violation against the structure? There are 2 ways in which this can happen. One is you can find a vertex x such that x has a neighbor in U1 and a neighbor in U2. If that's the case, then U1 and U2 cannot be a valid partition. So that's one way to find a violation. There's now a second way to find a violation. Either so you find an edge x1, x2, but x1 happens to be a neighbor of some vertex in U1, and x2 happens to be a neighbor of some vertex in U2. and this again would be a violation. So our goal with the rest of the queries is to be able to find one such violation. Okay. And remember, U1 and U2 create a structure. So what we're going to do is look at the set U1 and in particular spot all the neighbors of set U1. Let's call that set W2. Along with U2, we bunch that together and call it the set V2. Okay, and this is the one part of the partition of the entire graph, and all other vertices we place in V1. So U1 and the W1 shown here in orange together form V1. And here we're going to make a simplifying assumption that is certainly not true in general. But however, it helps to keep the analysis simple, and it's actually a fairly easy assumption to remove later. So we're going to remove that assumption as part of an exercise. But for now, we're going to make this assumption that every vertex other than the ones in U1 and U2 have a neighbor either in U1 or in U2. Okay. So the rest of the analysis is going to be based on that assumption. And let's recall that a vertex X would be a violating node, basically an evidence that this partition will not work as a bipartition if it is a neighbor to a vertex in U1 and also a neighbor to a vertex in U2. Okay. Or another way to find a violation would be a pair of vertices x1 and x2 such that both of them are neighbors of U1, so they actually have to be in set W2, but they end up having an edge between them. That's again a violation. And when either one of these violating structures are queried, the algorithm essentially eliminates this partition U1, U2. But keep in mind that there are a total of 2 raised to the cardinality of U number of possible partitions of the set U. Now, we must ensure that not only is this set U1, U2 is eliminated, we must ensure that our queries are strong enough to eliminate every possible partition of the set U. And keep in mind that this whole thing is operating under the assumption that the graph is in fact far from being an from being a bipartite graph, and so we need to the second part, the test part, should be strong enough to reject all these 2 power u possible partitions. Okay, and the goal is for each of these 2 power u possible partitions, we should be able to find a violating structure, either X or an edge x1, x2. Okay. Now, for this purpose, we set the test part. That's the set W, which is the next set of theta of epsilon to the minus 2 log 1 over epsilon number of vertices queried after the U, and we treat them as pairs because we want to get either an X or an x1, x2. For simplicity, we're going to treat this set W as pairs. So each pair could either include an X as an evidence against the bipartiteness, or include a pair x1, x2, which will again be an evidence against the bipartiteness. So now, what is the probability of not finding an X? So this must be an X, by the way. What is the probability of not finding an X or an x1 edge of the form x1, x2? These are witnesses against this particular partition U1, U2. In all of the 1 over epsilon squared log 1 over epsilon queries. This is the set of all queries in W, the second set of the test set. And that's going to be 1 minus epsilon raised to the theta of 1 over epsilon squared log 1 over epsilon, which we can work it out will be O of 2 raised to the minus U. And of course, with appropriate constants embedded into these theta notations, we can bring this probability down to a small constant. And this will be the small constant will be the probability of not detecting bipartiteness. Okay, so this gives us the overall idea. So in the first part, we basically remember we're focusing on graphs that are epsilon far from being bipartite, and the first part is the first set of U queries that we have basically enforce a structure, and there are now we focus on the 2 power cardinality of U number of partitions. You pick a partition, you ensure that with some very low probability, O of 2 raised to the minus cardinality of U probability, you ensure that the bipartiteness, we miss the bipartite, we miss finding evidence for the bipartiteness with such a small probability, which means that we will not detect the non-bipartiteness with, again, very low probability, even when we consider all the 2 power cardinality of U number of partitions. And so overall, the probability that we will not detect will be brought down to a constant, and that's a small constant, and that's our final goal, which we have achieved. But there are a few details that need to be worked out. So there are two exercises that we need to complete. First one, we need to reverse engineer the analysis to ensure that the algorithm detects non-bipartiteness with some reasonably good probability, say 5 over 6. And then that's fairly easy. And then the interesting challenge would be to remove the assumption that we made. Remember, we made the assumption that all vertices that are not in U are neighbors of U. And we need to ensure that that assumption is removed. And that will again be an exercise that we will work out. So that brings us to the end of our lecture on this enforce and test technique for property testing that especially is useful in the context of dense graph property testing problems.